Monday, October 5th, 2020 dynamics. That looks pretty good. Yeah, that's not too bad. Wonder if I had another light on here. Oh, gee, no, that's no good. I think that's all right. I'll leave it that way, maybe. Okay, well, let's see if there's anybody showing up here. Nope, it's just me. 5 minutes before class starts. And we'll have a short review of stuff we know. So let me put some review stuff up here. Okay. Topic. We'll review some things. How about work energy theorem? That'd be good. How about potential energy? That would be good. How about power? Efficiency? Power, efficiency. That's a pretty good start. And then we'll work some problems. Hey, we've got Ashley on board. Good morning, Ashley.
Good morning.
It looks like another beautiful day outside. No rain today, I don't think. Do you use a clothes dryer, or do you hang your clothes outside when to dry your clothes, Ashley?
I have a clothes dryer.
Yeah, we do too. But my mother had an outdoors, the old-fashioned clothes, kind of a pole with some wires, and you can, with clothespins, you hang up your clothes, and they really smell good after being out in the fresh air and sun. Work pretty good. Let's see who else we got here. Jesus, buenos dias.
Hello.
Hello. It's just the three of us right now. And we have 3 minutes before class starts. Do you guys have any questions for me? There is a test next week, test 2, and it's over chapters 13, 14, and 15. We probably need to get started on 15 here pretty soon, huh?
Yeah.
Yeah, we haven't really.
I actually have a question about homework, if you don't mind.
Yeah, go right ahead.
So I was actually late. I just fell asleep and missed turning in the most recent one from Saturday.
Yeah.
Do you still accept late homework for
Yeah.
partial credit?
Yeah, you'll have to put it in on the email though.
Okay, I was going to ask you that because I saw the link disappears afterwards.
Yeah, I think it's. Am I talking to Jesus or am I talking to Stuart?
Jesus.
Jesus, uh, you'll have to give it to me on email because I think once you miss the deadline on that link, I think it's over.
Yeah.
So just send it to me on email and I'll try to be nice.
Okay.
Good
Thank
for
you.
you. Yeah, anytime. Hey, we've got Stuart now too. Good. Unmute and say hi, Stuart. Unmute and say hi, Stuart. Well, he's here with us, and there's Braxton. Braxton's here too. We're getting a class now. Braxton, unmute and say hi.
Hello.
Hello. We got 30 seconds before class starts. Braxton, did you have any questions for me?
I don't think so. I think I understood it all.
Ah, that's wonderful. Good going. Well, I thought we'd have a little bit of review before we do some problems. Make sure that we understand this stuff. So I wrote down a few items there. The work energy theorem is pretty important. Well, let's start our class. Now, the way I write this work energy theorem is I go, the sum of all the works done is equal to the change in your kinetic energy of your body, or bodies in case there's more than one body. That's the way I like to write it. But now the book writes it differently. The book on page 86 writes it like this. But it says the same thing. See, what this is the sum of all the kinetic energies. You could put a sigma right here if you wanted, and that would say the sum of all the changes in kinetic energy. And see, if you put all the sum of all the initial kinetic energies and moved it over here and subtracted it, you would have the sum of all the changes in kinetic energy. And this is that's their secret symbol for work. They use U for work. I like W for work. I don't like U for work. I like W for work. And for kinetic energy, I like KE. The book has T for kinetic energy. But it's the same thing. They're just trying to confuse us, I guess. Now on potential energy, there's lots of different kinds of potential energy, but there's only two kinds in our book. There's only two kinds of potential energy in our book. Here, let me ask one of my excellent students if they know what the two kinds are. Hey, look at here, we got a whole bunch of wonderful students. Look at this. We've got somebody down here is, I can't pull up this last person. Dang it. Oh, there it is. Well, that's Stuart. I've already talked to Stuart, I think. Shane, unmute and say hi.
Hi.
Hi. Hey, Shane, do you know what the two kinds of potential energies are, the only two kinds in our book? Do you know what they are, Shane?
One's gravitational.
Yes, one of them is gravitational. Good going. Do you know what the other one is?
Spring.
Yeah, exactly. He's got it. He knows. Now, let me write that. Let's see. And see, if I was writing this, I would write potential energy. Now, for a spring, I'll put a little s there. It's 1/2 kx squared. Now, that x is how much the spring is stretched or compressed. That's your potential energy of a spring. Now, I think the book calls it elastic potential energy. It's elastic potential energy. Now, if the spring is already compressed or stretched before you start messing with it, then you have to subtract the initial amount. Put a little 2 here and a little 1 here. There you go. See, what that is a spring that's already stretched, and you come along and you stretch it some more. So you have to take and subtract to get the, well, it's really the change in potential energy, you know it? From its initial, whatever the initial amount of potential energy was. See, that's what that is. That's the initial. You could write this as your final minus your initial. Put a little I there if you can read my writing. So you'll see that in the book. Only they write it, let me show you how they write that. They write that on page 182. Page 182. Here, let me find that and show that to you. Page 182. We're having a little 15-minute review of some important things here, and then we'll work some problems. You're free to ask me any questions. But on page 182, here's the equation they write. They write this here. If you have your book, you can see that equation. I've just copied it down out of the book. But you see what they're writing. Hey, look, that's the same stuff. That's the same stuff I've got, huh? Yeah, it's the same stuff. Only, wait a minute, they got a minus in front of it, and I don't. I wonder why. Well, let me ask somebody. Instead of me just boring you, I'll ask somebody. Mark, unmute and say hello, please, Mark.
Hello.
Hello. Hey, Mark, I've got the same stuff here, but the book has a minus sign. Mark, how come they have a minus sign? Do you know?
Because the change in potential energy equals negative work.
Yeah, that answer is correct. See, what they really have here, this U is not potential energy. This U is their secret symbol for work. Remember up here?
Yeah.
Up here they got a U. That's their secret symbol for work. And so what they're saying is that the work done on the work done by a spring is equal to this right here. And I was telling you guys one day that there's a definition of potential energy that goes like this. This is a definition. It's the negative of the work done. That's what potential energy is. It's the negative of work done. And so if you got the work and you put a negative in front of it, okay, now just a minute, I'm getting confused now. Let's see. Yeah, this would equal, and then if you take the negative, yeah, there you go. See, if you take the negative of this, well, that makes the negative of a negative, it goes bye-bye, and so everything is okay algebraically. You see that?
Yes, sir.
And what my friend Mark just said was correct. And besides that equation, if you want to see it, it's on page yeah, it's on page, this equation is on page 215. If you go in your book on the 215, the only thing is the book, you know the book, they don't want you to understand this stuff, so they make it confusing. The way the book writes this equation here is like this. Believe it or not, this says the same thing. Now that U is the book's secret symbol for work. But these V's is the book's secret symbol for potential energy. I prefer PE for potential energy, but the book uses V for potential energy. Now what this is initial minus final. Well, what that would be is the negative of the final minus initial. If you rewrote this, you could say the work done is the negative of the change in potential energy. And remember, that's always, delta is always final minus initial. So if you have the negative of the final minus initial, what you're looking at is initial minus final. It's the same thing. They're correct. It's just that their notation is, I don't think it's as clear. Okay, well, we've talked about elastic potential energy, or as my friend, I believe it was Mark said, spring potential energy. That's fine. You can call it that if you want. But there's only two kinds in this book of potential energy, and the other one is gravitational potential energy. And it goes like this. And I'm sure you've seen that before. It's just MGH. But again, now the book writes that differently. The way they write that on page 181 is and they don't write it as potential energy. They write it as the work done by gravity. And the work done by gravity is negative of, see that W? In your book, W stands for weight. It stands for weight, not work. And so what they're really writing is minus mg delta y. Only I prefer h for delta y for the height that you lift something. And so the work done by gravity is mgh, but it's negative. See, if you lift something, the work that gravity does is negative. Now, if you're lifting something, the work that you do is positive if you lift something. But the work that gravity does is negative. But the change in potential energy, remember, is, where was that equation? Did I erase it? The change in potential energy, yeah, I erased it. I'll put it back. The change in potential energy is defined as the negative of the work done. So the change in potential energy when something is lifted up is positive mgh because it's the negative of the work done. There's the work done, and a negative of a negative makes a positive. But you know that. You know if you lift up a body, if you pick up something heavy, you're doing some work, and the gravity is doing negative work, but you're doing positive work, and the potential energy increases the higher you lift something. Well, I hope you're not totally confused. It's confusing enough that they had to change the symbols for things. And then there's power and efficiency. Let's talk about that a minute, and then we'll work some problems. Do you have any questions for me right now? Yeah, okay, we'll talk about power and efficiency then. And then we'll work some problems. Well, power, I talked to you about this the other day, and they explain it in the book pretty good, is equal to force times velocity. Now, if they're not going along parallel in the same direction, and of course they're vectors, velocity is a vector, force is a vector, then you have to use a dot product. But notice you don't put a vector sign over power. Now, let me ask one of my wonderful students. Let me go to my friend Ashley. Ashley, help us out here, Ashley. Why don't I have a vector sign over that power, Ashley? Tell us.
I'm not sure.
That's okay. That's fine. Ashley, the reason is that we don't have a vector sign over power is not a vector. Did you know it's not a vector?
No.
It doesn't have a direction. Now force has a direction. You know, it can go up or down or any direction whatsoever. And velocity has a direction. You can go north or south or whatever, up and down. But power is, now Ashley, I know you know the answer to this. If something is not a vector, what is it? I'll give you a hint. It starts with S.
Scalar.
Yeah, good going. See, power is a scalar. It's a scalar. It does not have direction. Did you know, I'm asking everybody now, I'll quit picking on Ashley. Did you know that this here has got a name? It's called the scalar product. It's called the scalar product. It's a vector thing. Oops, product. Now they have other names for it. They call it something else. Inner product. I think they call it an inner product. And they have a third name, scalar product. Oh, I like to call it the dot product. It's the dot product. Scalar product, inner product, dot product. There's a lot of things that are scalars, like for instance, money. Money is a scalar. Energy is a scalar. Potential energy is a scalar. I bet we could think of a lot of others, but right now my mind is just blank. But there's power. Now let's talk about efficiency. Unless somebody has a comment or question, here's your chance. Okay, well, let's talk about efficiency. They use a Greek letter, lowercase epsilon, for efficiency. And what it is, it's the output power divided by the input power. By definition, you put a little third line there, it's a definition. Now, you could write it as output work divided by input work. That'd be okay. Because remember what power is, it's just work per time. So if you divide by time, you got power. Well, that's what efficiency is, and that concludes our review for now, and now we're going to work some problems. Did anybody have a question? Okay. Well, let's do F1410. Let's do that. And we'll get started on chapter 15 sometime Wednesday morning. So we're on schedule pretty good. Now this is F1410. Now I have to find it now. It's on page 208. Yeah, there we go. We have a block that's being pulled up a hill. It's a 30-degree hill. Hey, you know what? I could actually measure that 30 degrees. Let me do that. I'm going to actually measure this 30-degree hill here, and I'll get my protractor and I'll put it right there. Yeah, there's 30 degrees right there. Do you do that? Do you actually measure stuff, or do you just sort of guess what it is? You're supposed to measure stuff. Okay, we've actually measured that. You're looking at 30 degrees there. And you have a block there that's being pulled up the hill. Let me draw that. Coefficient of, I'm on page 208. Coefficient of kinetic friction. It's a 20 kilogram block. 20 kilogram block. Coefficient of friction, kinetic friction is 0.2. Let me write that down. And the block is going up the plane, a constant velocity of 5 meters a second, and it's constant. And it's got this force. Now I like to put my forces in red, so let's put a red force right here. But we don't know what it is. We're supposed to find it. But let's put our other forces on here. Well, we have 20 times 9.81. I should know that by now. Is that 196.2 newtons? I don't trust myself. 20 times 9.81. Yeah, I got that right. How about that? 196.2 newtons. And then you have a normal force here. Put your forces in red. And that normal force you can get by taking the sum of the forces in the y direction. So you could have this be the x direction. And this could be the y direction. And the sum of the forces in the y direction is 0. So the normal is equal to 196.2 newtons cosine of 30. Let me get that. 196.2 times cosine of 30 is 169.9. Okay. See, that's the normal. We got that figured out. And now see, we can get the friction. It's kind of going like this. There we go. There's the frictional force. And the frictional force is 0.2 times the normal, which makes it 33.98 newtons. See, that's kinetic friction. It's got an equal sign. Kinetic friction. Now, if you were talking static friction, it doesn't have exactly an equal sign. It has a less than or equal to sign. It's not near as nice as the kinetic friction because less than or equal to, that really doesn't pin things down very good. But we don't need to worry about that because we have got motion, we've got kinetic friction, and we have drawn our free body diagram, and we put in our red stuff. But what about the green stuff? Well, let's do that. See, going this way, you could put in, I don't know if that shows up green on there. Probably, yeah, kind of. That's your u of x. And you don't really need a u of y, but you could put one in. Wouldn't hurt anything. There's your u of y. Those are called unit vectors. So here's the way you do these problems. You draw the free body diagram, put in the red stuff, the green stuff, and then you start using your equations. Like, for instance, Newton's second law. I think we want Newton's second law. Well, now they really want the power, but we can get it. First, we're going to use Newton's second law. All right, here goes. the sum of the forces in the x direction equals the mass times the acceleration. But see, the acceleration is 0. They said the velocity is constant. And what acceleration is the derivative of your velocity. And you guys took calculus. So the derivative of a constant is 0. So the sum of the forces in the x is 0. Well, let's write them out. Here goes. We have F is in the x direction, and friction is in the x direction. Now, how much is friction? It's the 33.98 newtons. But we have another force in the x direction. See this 196.2? It's got two components. It's got one, well, it's really in the negative x direction, isn't it? And plus it has one going this way in the negative y direction. But the one we want is the negative 196.2. It'd be sine of 30. Can you see that? Or cosine of 60, if that makes you happy. We'll put cosine of 60 in there. Do you know the cosine of 60 is equal to the sine of 30? And it's equal to 0. All right, we're going to solve that and get our... I did that wrong. This stuff goes up here. Let me write it where it belongs. I goofed up there. I did that wrong. This here doesn't go there. Okay, now we can solve for friction. No, not friction. This rope. Somebody's pulling on a rope. And the force that they're pulling on that rope is equal to I'm just plugging in these numbers now. I'm getting 132.08 newtons is the force. Somebody's pulling on a rope there. And if you want the power, did you know for every force, you could talk about the power. You could talk about the power for every force. And for this force here, the power is equal to F times the velocity. We have the force, we have the velocity. The velocity is 5 meters a second. And so the power is the force in newtons times your 5 meters per second. That'll give you joules per second or watts. Here goes. I'm going to multiply by 5. I'm getting 660.4 joules per second. Or you could just call it watts. How's that? I think we're done. I think we did it there. Now, I don't know if they want horsepower, but if you wanted horsepower, remember the way it works is, we'd have to convert that. We'd have to convert that. That'd be kind of fun to do. Let's do that. See, do we have room here? Yeah, we got room here. See, what we're talking about is a watt is a Newton meter per second. Now, in the flap of your book, in the very, very front flap of your book, it says it says a pound is 4.448 newtons. And it says a foot is 0.3048 meters. So see, we could get rid of the newtons and the meters. See, look here, the newtons, we could get rid of them. How about that? And the meters, we could get rid of them. And we can have foot-pounds. And then if you wanted horsepower, the way it works is a horsepower is equal to 550 foot-pounds per second. See, right now we're going to have foot-pounds per second, but we can get rid of the foot-pounds per second and get horsepower. Just for fun, we're going to figure out the horsepower. Here goes. Okay. You take 660.4 watts. You'll have to divide it by these three numbers. Here goes. I'm going to do it. 4.448, 0.3048, 550. I'm getting, I don't know if that's what they want, but it's 0.8857 horsepower. Okay, now let's look in the back and see what they said the answer was. But we just did fundamental problem 1410. And I'm going to go back here and see if they have 1410. Nope, they just said, the book says 660 watts, and that's all they did. They didn't figure the horsepower. Okay, good. We might want to figure out what 1 watt is in horsepower, just for fun. Let's do that, and then we'll move on. 1 watt is equal to 1 divided by 4.448 divided by 0.3048 divided by 550. I'm getting 1 watt is equal to 0.00134 horsepower. Or you could flip that, take the reciprocal, and you could write it this way. Is there enough room right here? There's barely enough room. 1 horsepower is equal to 700 and, I'll round it off, 746 watts. You might want to Google that to make sure I didn't foul up too bad. But we have just done fundamental problem 1410. Do you have any questions? Okay, well, let's do a different one, shall we? We're going to do a different one now. Turn to page 209 if you got your books handy, or your e-book. This is an interesting problem. It's a person running up some stairs, and it'd be fun to figure their horsepower. Now, I actually do this every semester with my students when we have regular face-to-face classes. We go down the hall, and I'll get a volunteer, and we'll have a stopwatch. And we'll get a yardstick, and we'll measure how much each step is. And I forget what it is. It's something like 9 inches or so. You know, the steps going up to the second floor there at TJC. We count the steps from the first floor to the second story, from the first story to the second story. And if you know each one's 9 inches, then you can figure out how many feet. And then we'll have our student run up the stairs. We'll time the student with a stopwatch, and we can figure out their horsepower. Now, I've had some students that are pretty athletic, and they were able to generate over 1 horsepower. Now, that's pretty good. It gave them an appreciation of what 1 horsepower is. It takes a lot of effort for a person to generate 1 horsepower. And you know what? A horse can generate 1 horsepower for an extended period of time. I don't know how long, maybe all day. They're powerful animals. But let's do this problem. This is problem 1448. But I usually let 3 or 4 students try it, and most students come short of a horsepower. I didn't make it. I think I got something like 3/4 of a horsepower. I didn't make it to the 1 horsepower. Okay, now this person here, 1448, a man having a weight of 150 pounds, is able to run up a 15-foot high flight of stairs in 4 seconds. So he's 150 pounds. He runs up 15 feet. And he does it in 4 seconds. And now what we're going to get here is foot-pounds per second. All right, let's do that. Tell you what, I have all the fun in here. I want you to have some fun. I want you to give me the foot-pounds per second. Go ahead. I'll shut up. And then I'll ask one of you guys. Okay, now let me ask one of my excellent students here. We have, well, I think I'm missing some of my excellent students. But let me pick on Stuart. He's a good sport. Stuart, unmute and say hello, please.
Hello.
Stuart, what'd you get for your foot-pounds per second?
562.5.
That's what I got. Now, Stuart, what I want you to do, I want you to convert that to horsepower. Do you know how to do that?
Yes, I got 1.023.
That's what I got. I got 1.023 horsepower. Does anybody need help with that? Okay, well, we did great. I bet that's the answer. Then they said, determine the power. Well, we did that. How long would a 100-watt light bulb have to burn to expend the same amount of energy? Let's do that. That'd be fun too. You're all familiar with 100-watt light bulbs. I might have one. I bet that's 100. I bet I have a 100-watt light bulb lighting up this whiteboard right now. You see what that is that's 100 Newton meters per second. You see, a watt is a joule per second, and a joule is a Newton meter. Okay, well, let's do our little trick that I just did. I shouldn't have erased it, but in the flap of your book, let me get this out of here. Yeah, in the flap of your book, the very front flap of your book, they tell you that that a Newton is what they tell you is a pound is 4 point. We just did this, but I shouldn't have erased it. Is that many newtons? And then a meter, they tell you that a foot is 0.3048 meters. So see, you can get, well, you can get the newtons to cancel and the meters to cancel, and you can get your foot pounds. And then you can get your horsepower, can't you? You can get your horsepower. Is that what they want us to do? Let me read this again. How long would a 100-watt light bulb have to burn? Okay, well, we'll get that in a minute. But right now, let's get our foot pounds per second. This will be foot pounds per second. Okay, well, that's 100 divided by 4.448 divided by 0.3048. Did you get 73? Somebody check me on this. Make sure this is right. 76 foot pounds per second is a 100-watt bulb. Okay. Now they want to know what time period will give you the same energy. Isn't that what they want, the same energy? Yeah. How long will a 100-watt bulb have to burn to expend the same energy? Well, a 100-watt bulb is 73.76 foot-pounds per second. Now, if you wanted the same foot-pounds, isn't the foot-pounds 150 times 15? So you see you got 150 times 15. That's your foot-pounds that the person used up, I guess you might say, to get up those stairs. And that's going to equal 73.76 foot-pounds per second times your time in seconds, right? See, you'll get foot-pounds equal to foot-pounds. Do that. Solve for the time. Here goes. I'm getting a time of 30.5 seconds. If you have a 100-watt bulb and you turn it on for 30 seconds, the amount of energy you use up is equal to the amount of energy that man used up to climb those stairs. Okay, well, that was fun. Let's do another one. Do you have any questions on that? All right, well, let's move on then. Let's do, let's do 1422. Let's see if I can find where that is. Here we go, 14. Yeah, this looks like fun. 1422. Any comments or questions so far on anything? No, all right. Well, what were they trying to teach us here about this light bulb that you turn on for 30 seconds? I think the moral of the story is, gosh, that's just 30 seconds. It takes a lot of energy to climb those stairs. You're huffing and puffing when you get to the top, right? So that's a lot of energy. And I guess you could say the light bulb is using up a lot of energy. And in a half a minute, you use the same energy? Are you kidding me? I mean, you have that light bulb on sometimes, I don't know, in your hallway or kitchen or whatever. You might have that light bulb on all day long. Hey, people around here, I'll talk softly, I don't want to get in trouble, but people around here leave light bulbs on. They're gone. I go down in the hallway and turn off bulbs because, see, I got to pay for the electricity. They leave light bulbs on all day long. Think of the energy that they're not getting any benefit from. They're wasting energy, aren't they? Think about it. In a half a minute, that light bulb used up the same energy that man used up climbing those stairs. Think about the energy involved if you leave the light bulb on all day long. So the moral of the story is, if you read the problem, we did 1448. It says something about, for heaven's sakes, turn off the lights. You do know that most of our energy comes from coal, and they have to burn that coal to provide us with energy. So they're burning coal, and we're burning this energy, and the lights are just not doing anybody any good because nobody's home. We just left the lights on. Well, I hope that was entertaining. Let's look at this one now. This is 1422. And what they've got there is they've got two springs. And they have a mass. How much mass? 25-pound block. And over here, they got another spring. There we go. And they said this is got a spring constant of 10 pounds per inch. And this has a spring constant of 60 pounds per inch. And they said the block is going 10 feet per second. It's moving 10 feet per second. And the distance here is 1 foot. It looks like this distance is 1 foot to here, and it looks like it's 1 foot to here. You're kind of in the middle there. Okay. And the coefficient of kinetic friction is 0.4. Is there anything else? Did I miss anything? Yeah, that's pretty much it. Now here's what's going to happen. It's going 10 feet per second, but there is some friction, so I think it's going to slow down a little bit. It's going to slow down, and then it's going to hit that spring, and it will compress that spring, and then it'll bounce back. Now it's going to go back this way, but now as it goes back, won't it slow down because there's friction? Yeah. And so when it gets to here, it's probably going pretty slow. I don't know, 10 feet per second, that's, let me see what that is, just a minute. Well, that's only about 7 miles an hour. That's only about 7 miles an hour. Not that terribly fast, but I think it's probably going fast enough that it'll come here and it'll hit that spring, compress that spring and bounce back, and it'll go this way. Now, I'm not sure how many trips it's going to take, but eventually it will slow down and come to a stop. Now, what do they want to know? Let me read this. Determine the total distance traveled by the block before it comes to rest. Okay. Now, in our review, I didn't give you your conservation of energy equation. But we can't use it anyway. We can't use the conservation of energy equation because there's friction. Didn't I tell you guys? Here, let me review you on that. There's a wonderful equation that's called the conservation of, and they really should call it mechanical energy, but they just call it energy, the conservation of energy. And what they said was, in fact, I showed you where this came from. It comes from this. The sum of all the initial potential and kinetic energies is equal to the sum of all the final potential and final kinetic energies. If, and there's a big if there are no non-conservative forces that do any work, like friction, for example. See, friction's doing some work, so you can't use it. This only works if the only kinds of potential energies you have are gravitational and elastic. If all you got is gravitational and elastic energy and no other forces that do any work, no other forces. You can have gravitational forces, you can have spring forces, but if you have any other kinds of forces that do any work, you can't use it. That's why I put a skull and crossbones on this equation. Beware, beware, Halloween is coming up. Beware of that equation. We can't use it, so what do? You can't do that. Forget it. Let's just subtract it. We can't get rid of it, or we can't use it. Hey, you can use this one. I want to see if any of my wonderful students know the name of that equation. Let me go to my friend Shane. Unmute and say hello, Shane.
Hey,
Hey, Shane, you see this equation here? This is this equation right here is the second most important equation in our whole course. What's the name of it, Shane?
the work energy theorem.
Yay! right, good going. He's been awake and alert, and he knows. And you got it right. Now this equation here, it doesn't have a skull and crossbones. I'm gonna put a happy face. It always works. It's the work energy theorem. And so what we're going to do is we're going to use that. Now, it's true that each one of these springs does some work on the mass. Now, when that spring compresses the mass, the spring is pushing to the right, but the mass is moving to the left, so that's negative work. And then when the spring rebounds and pushes on the mass, the spring is pushing to the right and the mass is moving to the right, so that spring is doing positive work. Every collision with the spring does the equal amount of positive and negative work, so the springs don't do any total work. The total work done by the springs is 0. I'll go over that again if you want me to. Does anybody need me to go over that again?
Yeah, would you one more time?
Yeah. See when, like this mass here it comes. It hits that spring, and that spring compresses. It all compresses, and see the mass. You understand the mass was going to the right, but the spring is pushing it. Put a red arrow there. See this, the force of the spring is during the collision when the thing is coming in, the force of the spring is going that way, but the velocity was to the right. Well, that's negative work. Remember, work is a force dot product with your distance. Well, it's really an integration because the force varies as the spring, it actually increases as that spring tightens up and gets more compact. It pushes even harder. So it's really a dot product, but it's negative on the way in. But now on the way out, the spring is expanding. And when it rebounds, well, the spring is still going, the spring is still pushing that way. It doesn't push the other way, it only pushes that way. But now the velocity is this way. So see, the spring is pushing this way, the velocity, the distance it pushes is this way. And that's positive work. They're exactly equal. They're exactly equal because remember the work done is 1/2 kx squared. K, the x is the same. Whatever this thing compresses, that's how much the x is. And when it expands exactly the same amount. So the spring does 0 total work. Every time it has an encounter with a spring. Now somebody just asked me a question. Who was that? Was that Mark? Somebody asked me to go back over that. Who was that?
That was me,
Yeah, now tell me your name again.
Shane.
Shane, yeah, thank you, Shane. Shane, do you understand now why the springs do 0 total work? Do you understand now?
Yeah, makes sense.
All
Thank you.
right, good going, good going. Well, the springs don't do any work. And there are other forces. There's the weight and there's the normal, but they don't do any work because they don't do any motion in the y direction. The only thing that does any work is this friction. And it'll be a negative times the friction, which is 0.4, times the normal, which happens to be 25. It's equal to the weight, times the distance it travels. I don't know, you want to call it maybe S maybe. That's it, guys. That's the total work done by friction. It's negative because whenever it moves, the friction's in the opposite direction. And this is going to equal the change in its kinetic energy, which will be the final, when it comes to rest, minus the initial, which is 25. Getting mixed up now. 1/2 mass. Yeah, but see, you have to be in slugs, remember? And what is it? 10 feet per second squared. There's our equation. Kind of got messy. Let me write it down here. What we're writing is the total work done is equal to the final minus the initial kinetic energy. The final work done, the only thing that doesn't work is the friction, and it's negative 0.4 times the normal, 25 pounds times the distance it travels. I don't know, delta x. Well, there you go, delta x. That'd be better. We'll put that in there, delta x. There you go. And this is going to equal the final kinetic energy, which is 0, because it finally quits bouncing around and stops, minus 1/2. But see, you got to put the mass in there. Do I need to explain slugs again? I think I explained it once. But see, mass is not in pounds, it's in slugs. So here's our equation, and we're going to solve for your delta x. Put that in your calculators and find out how far the total distance that thing travels. And I'll shut up for a minute. Go for it. Okay, let me pick on somebody here. Braxton, what'd you get for the total distance this thing travels?
I got 3.88 feet.
That's what I got. Now, I don't know how many times it goes back and forth, but whatever a number of times it is, we could figure it out. 3.88 something. What are the units, Braxton?
Feet?
Yep, good going, feet. Well, think about it. Goes 1 foot here, plus a little more now when it compresses the spring, and then the spring rebounds, plus 1 foot. Well, that's 2 plus something there, and then here there's another 3 foot plus something, and I think it squeezes that spring a little bit, bounces back, and somewhere in here it stops, and that's it. It doesn't bounce a whole bunch of times. Now let's see how we did. This was problem 1422. We're going to go in the back and take a look. 1422, and it says 3.88 feet. The book says 3.88 feet. So they just rounded off. And we're pretty happy with that. Anybody else have a comment or question on the problem 1422? Okay. Now you have some homework. You always have homework, but it's on Blackboard. Just look it up and do it. Submit it on time. Okay, let's do one last problem. Unless you have a comment or question, I'm going to erase all this. All right, we'll say goodbye to all that. Okay, we're looking at, I want to do 1495. 1495. Now let me find it here. 1495. Let me shop around here. Anybody know where it is? $14.95, trying to find it.
Page 230.
Thank you so very much. Yeah, there it is, $14.95, got it. The cylinder has a mass of 20 kilograms, is released from rest when H is 0. Okay, I think what we've got here is a spring, and there's a weight here of 20 kilograms. And then there's a spring here. And these distances are 2 meters and 2 meters. They release it from rest, and it goes down 3 meters. Okay. Now these springs have a spring constant of 40 newtons per meter. Let's review that spring constant business. Oh, gee, we only have 10 minutes left. Better make it quick. There's an equation that goes like this. It's called Hooke's law. Now, if you're talking about an outside force, then it looks like that. But if you're talking about the spring, the force that the spring is applying to a body, it's like that. There's a negative sign. Because, see, the spring, if you expand the spring, it pulls on you. It's always opposite. If you compress a spring, it pushes back. It's always opposite. Take a spring, no matter what you do to it, the spring opposes what you do to it. You pull on it, it pulls back. You push on it, it pushes back. There's a minus. And so you got this spring here, and it's going to have a force on it. And this thing is going to go down 3 meters. Well, that'll put you down to about, I don't know, about here. Your 20 kilograms is going to be down here. And see, what will happen is this spring will be stretched. It's going to be stretched. And I can tell you how long that is. If this is 3 meters from here to here, all the way up to the top, then that would be the square root of 2 squared plus 3 squared. That's the square root of 13, right? Yeah. Okay, now how much is that? Well, the square root of 13 is This is 3.605, bunch of fives, meters. Okay, now they said that the spring is relaxed at 2 meters. So if you wanted to know the force of the spring, like when it's down here, that would be minus K, which is 40. But see, you'd have to subtract the 2 from it. So it would be 1.6055. Hope you can read my writing. I'll tell you how much that is. 1.6055. You understand that? See, 2 meters is not stretched at all. At 3.6055, if you subtract the 2 meters, you'll get the 1.6055. That's how much the spring is stretched. And the force of the spring will be 40. 40 times 1.6055. I'm getting that this spring right here, down here at the bottom, this one's pulling with a force of 60.22 newtons. Of course, this one is too. That's pulling with a force of 60.22 newtons. Need a newton there. Haven't lost you yet, have I? Everybody okay? Yeah, we got 5 minutes left. Now, what do they want us to do here? Just a minute. Let me read this. It's released from rest, and when it gets to 3 meters, find out the speed. Okay. Now, in this problem here, you get to use the conservation of energy, conservation of mechanical energy, because the only 2 forces acting on this thing are the spring and the gravity, which would be 196.2 newtons. And so you have gravitational potential energy and you have elastic potential energy. There's no friction. There's no other outside forces. You get to use it. Yay, we get to use the conservation of energy. Let me find some room here. We'll put it up here. There it goes. If for anybody that just tuned in, we're doing problem 1495. It's on page 230. Page 2. It's on page 230. And here's the plan. We're going to take the sum of all the initial potential energies and the initial kinetic energies, and that's going to equal the sum of all the final potential energies and the final kinetic energies. But now the thing is, there's 2 kinds of potential energies. There's gravitational and there's elastic. Now the initial elastic potential energy is 0. It doesn't have any because the springs, remember, are not stretched or compressed to start with. Their relaxed position is 2 meters, they said. Oh, gee, we need to hurry up. But we have gravitational potential energy equal to the mass, which is 20 kilograms, times mg, 9.81 meters a second squared, times 3 meters. And then the initial kinetic energy is 0. And there's your equal sign. And here comes the final potential energy. Well, it would be 1/2. Well, actually, there's two of them. So it'd be 2 times 1/2. Oh, gee, what they say that the K is 40 newtons per meter times that distance squared, 1.6055 squared, plus the potential energy, gravitational potential energy is 0, plus your final kinetic energy, which is 1/2 the mass, times the velocity squared. Okay, now here's your equation. I hope you understand all these terms here. This is your elastic potential energy. There isn't any. This is your gravitational potential energy, mgh. This is your initial kinetic energy. There isn't any. It starts at rest. Now there's 2 of these elastic potential energies. So you have to multiply by 2, 1/2 kx squared, plus your gravitation. You lost all your gravitational. You had gravitational energy, but when it gets to here, it's gone. So that's 0, plus your final kinetic energy, 1/2 mv squared. Now we have 55 seconds left in our class. Tell you what, you guys plug that in and get the velocity, and I'll look up the answer in the answer book. On your mark, get set, go. Plug that in, and I'll write down the answer book here for $14.95. I'm looking it up here. They said the answer is 6.97 meters a second. I'm going to do it too. You do it, I'm going to do it. We'll see if we get that answer in the answer book. 20 times 9.81 times 3. Then what do? You subtract. Boy, Jove. This is the book answer. And when I plugged in that equation, what I got was 6.9677 meters a second. I'm pretty happy with that. It looks like they rounded off, huh? Anybody get that? Say, uh-huh.
Uh-huh.
Yeah, there's one. I need another uh-huh. I need another uh-huh.
Uh-huh.
Yeah, there's one. Good going. Okay, well, you've got your work to do. And next time, ask me some questions and we'll continue on with this stuff. But we want to start 15 a little bit next time. So you might want to read ahead a little bit on chapter 15. That's impulse and momentum. But right now, our time, oh, it's sad, but our time is up. Here's your last chance to say something, and then we're going to sign off.
Have a good day.
Hey, you have a good day. Be careful. We'll see you on Wednesday at 9:30, right? Yeah, that's it. Well, bye-bye, students.
Bye.
Bye-bye. Adios, muchachos.